Hello and welcome to Module 9 in our C language series. Today's session is going to focus on file I/O. Just a little background, we know from the previous session there are no I/O statements in C. Rather, we use calls to functions to execute I/O operations, but it's this very design that makes C's file I/O system extremely powerful and flexible, allowing us to share data easily between devices. The data could be either in binary format or text format. The basis of C's file I/O system are streams and files. So what exactly is a stream? Let's say we have a file on disk and we want to display the contents on the screen or the console if you like. When the file is opened, a logical connection is established through which bytes can flow from the disk to the console, and this connection remains open as long as the file is open. The moment the file is closed, the connection is closed as well. That essentially is what is called a stream. But it's the concept of the stream that keeps the programmer independent of the device they're reading from or writing to, right? So in essence, it provides an abstraction between the programmer and the device, therefore allowing us to use the same function to write to the terminal or to a disk drive, for example. Now coming to the types of streams, we can have text streams and we can have binary streams. Looking at the characteristics of each, text streams will have lines terminated by an optional new line character. Certain character translations may occur as a result of the host environment. These would include, for example, maybe a \n or what is called a single line feed, or a new line character being translated to a combination of carriage return plus line feed when writing to disk, and then when reading from disk, the opposite will occur. Therefore, because of these translations, there need not necessarily be a one-to-one relationship between characters read or written and those on the external device. Talking about binary streams, though, it is a sequence of bytes with a one-to-one correspondence to those on the external device. No character translations occur. The number of bytes is the same, read or written. However, null bytes may be appended. Why? This is the surface of a disk. What's marked in red is called a track. What's marked in yellow is a sector as indicated on screen. Important to note that physical writing on disk is done in sectors. So if we have a file of 3 KB size, how many sectors would it need? Considering each sector would store 512 bytes. Just to digress a bit, currently a sector can store 4096 bytes, but we're not going with that value. That's called the advanced format, but as I said, we're not going with that value. We're sticking with 512 for ease of understanding. Now, having said that, what is the number of sectors that would be needed to store this file? Do the simple calculation and we get 5.85. But sectors don't work with fractions, more like whole numbers. And so that would need 6 sectors, right? And so we can actually store 3072 bytes. But our file is 3000 bytes. So what about the 72? Well, that's when null bytes may be appended. And again, this is dependent on the implementation itself. Coming now to files, a file could be a file on disk or a file on a terminal or a file on printer. Now, having said that, for the purposes of our discussion today, we're going to stick to files on disk. We saw from the previous slide that an open operation on a file creates a stream. Once the stream is open, the information can be exchanged. As each character is read, the file position indicator is incremented. What is the file position indicator? We'll see shortly. A close operation disassociates a file from a specific stream. Important to note that all streams are the same, all files are not. Why are all files not the same? Well, because files are associated with their devices, right? We'll have a file on disk, which is different from a file on a terminal, which is different from a file associated with the keyboard, right? So the capabilities of these files therefore will be different, because a printer, remember, has different capabilities than a disk has, for example, or a terminal has different capabilities than a disk has. Streams are the same because, remember, it's the logical connection, and that's going to be the same irrespective of the device. Coming to now the file position indicator, think of each of these segments as being 1 byte. When the file is opened, the file position indicator is positioned at the top of the file, and as we read each byte, that file position indicator moves across the file, progressing through the file until, of course, it reaches the end of file when the file is closed. This leads to the next point of discussion, which is types of file access. We could have sequential access or random access. Sequential access is what we just saw. That's reading 1 byte at a time, right? Moving across until we reach the end of file. With random access, however, we could jump bytes, so we could read the third byte directly, right? And this is possible, of course, only with disk files, random access, that is. Coming now to what happens when a file is opened. This is just summing up. A stream is open for use. A file is linked to the stream. What happens when a file is closed? The file is disassociated from the specific stream it was connected to. If opened for output, all contents of the stream are written to the external device, which means, in essence, that stream is flushed. Now, we've used flush before, if you recall, with stdin. And we see in the session that stdin itself is also a stream. Important to note that all files are closed automatically when a program terminates, either when main ends or exit is called. But having said that, it's important to close your files through code. Files are not closed when a program crashes, which leads to corrupted files. How does the file I/O system actually work? So now we're getting down to the nuts and bolts of how this all comes together. Every stream associated with a file has a file control structure. We've learned about structures before. It's exactly the same concept. The type of that structure is file, and it is defined in stdio.h. Important to note that we should not change the structure, because if we do, we could have unpredictable results. There's also other constants that are defined in stdio.h that are relevant to the file I/O system. These are end of file or EOF, seek set, seek current, seek end. EOF pertains to both sequential access as well as random access when we're talking about disk files, but seek set, seek current, seek end are specific to random access. Coming now to the file pointer, we've spoken about the file position indicator. What is the file pointer? It's a pointer variable of that type file which we spoke about earlier. Remember, file is a structure defined in stdio.h, so the pointer will be a type of that structure. Stores information about the file, which includes the name of the file, and therefore can identify a specific disk file. Is required to be used by a program in order to read or write files. How do we define it? Just file star fp. Coming now to file system functions, or the file I/O system functions. fopen, fclose, putc and fputc. As you can see, write characters to a file. getc and fgetc, read characters. fseek again is particular to random access and seeks to a specific byte. We have fprintf, which allows us to write formatted data to the disk, and fscanf allows us to read that formatted data from the disk. feof, now you may say, why do we need feof if we already have end of file defined as -1 in stdio.h? The reason is to accommodate binary data files. Note that -1 could be valid binary data. In order to prevent the compiler from misinterpreting that valid binary data as end of file, there's feof provided by C. ferror returns true if an error occurs. Rewind allows us to reposition, in a sense, the file position indicator so that it's now at the beginning of the file. Remove erases a file. Flush flushes a file. As I said earlier, we've used flush with stdin, but we can also use it on a file. Coming now to fopen, which is the actual function that opens a stream for use and links a file to that stream. Returns a file pointer associated with the file. You can see the prototype there, returning the pointer of file type. Takes as parameter file name, which is a pointer to string of characters which could include the path to the file, as well as mode, which is how the file will be opened. On error, fopen returns a null pointer, and we need to check for this every time we use fopen. A text file open in read mode may have carriage returns plus line feed combinations translated to new line or single feed characters. Remember, new line and single feed have the same ASCII code, which is 10. And of course, the opposite will happen when writing to files. To modes now, we have R for opening the file for reading, W for writing, A for appending, in which case the file position indicator will be placed at the end of file, which means we cannot really read this file. Right? We can append to it though. RB opens binary file for reading. So if there is a file already existing, it will open that file. WB though will create a binary file, and this is important. It will erase any existing file, WB that is, and create a new file. AB appends to binary file. R plus opens a text file for read write, but W plus creates a text file, again erasing any existing file. A plus appends or creates a text file. What's the difference between A plus and A, you may ask? Well, with A plus, the file position indicator is placed at the beginning of file, so we can read this file as well as append to it, unlike with the A mode. R plus B opens binary file for read write. W plus B creates a binary file, again erasing any existing binary file. A plus B appends a binary file for read write. So how do we actually write this fopen in code? We need, of course, to define our file pointer first and then use that file pointer to catch the return value of fopen, right? And we provide to fopen the two arguments, which is the name of the file and the mode. Now you see how the file pointer is linked to the file. Coming now to fclose. Close is a stream that was opened by a call to fopen, writes any remaining data to the file. Does an operating system close on the file? So you see now that the operating system itself interacts with these input-output functions. Freeze the file control block associated with the stream. File control block is again an operating system concept, but when we're talking about files in a program, this file control block will exist in program memory, right? And therefore needs to be freed by the program. OS limit to how many files can be opened. There is an operating system limit on how many files can be opened at one time, and we'll see how we can check that through code shortly. The prototype for fclose returns an integer, takes as parameter the file pointer. The integer it returns will be 0 when successful, and any other value for error. What happens if a stream is not closed? Well, we could have lost data or destroyed files or program errors. Therefore, it's important to include fclose in your code. Writing a character, we use putc or fputc, both yield the same results. If successful, they return the character written, otherwise end of file. The prototype is like this, returning an integer, taking as parameter again an integer type, as you can see there, and the file pointer. Important to note that although ch is defined as int in the prototype, only the low order byte is used, and we've seen why in the last session. Reading a character, getc and fgetc returns end of file when end of file is reached or when there's an error. The prototype again, int getc, returning an integer as you can see, and taking as parameter or argument the file pointer. Here it's important to note that getc returns an integer, but again the high order byte is 0 if of course getc is successful. And we know why, right? Because just to repeat that the character will be in the low order byte. Therefore, the high order byte is 0. Write some code, write a program to read characters from the keyboard and write to a disk file and accept the characters, of course, until the user enters a $. So let's now go to code blocks and start a new file. But before that, I'm going to show you how to check the number of files that can be open at once. So here we are using this function _get max stdio, which is defined in stdio.h, and you'll find this in the Windows documentation specifically. So now if I run this, we'll get the value that indicates the number of files that can be open at one time. You can change this value, but that's a discussion for a later date. Moving on now to write our code. So let's start a new file. So now we start with #include stdio.h and then #include stdlib.h. These are all the header files we need. Int main, we're going to use command line arguments, so int argc, comma, char argv. We need a file pointer, so file char fp, and then char ch. We check if argc is not equal to 2. Remember, the first argument will be the program name, printf, file name required, and then exit 1. Next check will be for fopen. So if fp equal to fopen, and the file name is going to come from argv1, we're going to open it in write mode, and that's equal to null. Then printf error opening file exit 1. If this goes through, all we need to do is accept characters. So we'd have a loop while ch not equal to $. And here we're going to use getc because we're not really working in an interactive environment where those characters need to be changed to something else as we type them in. So ch equal to getc. And now we can use putc or fputc, ch, fp. That loop will go on as long as the user does not enter a $. Once that loop exits, all we need to do is close the file. Let's build this now because we need to run this from the command prompt. There is some error at line number 4. We've not put in character there. Right, so now we need to go to command prompt. Right, we need to change directory to where our program is. And now we can type in the name of the program. Test for error, and we get the error printed out there. Press the up arrow to go back to the command and type the name of our file. Let's call that new file. And it's ready for entry. So we can say right, and now if we enter a $, that's the end of the file. We can use the operating system command type and the name of the file to see if the contents are there. Right, so that's created a file now. Let's move on. Write code to read characters from the file that was just created and write them to the console. So what we're going to do now is go back to code blocks and we start a new file. And what we're going to do is just copy that code because it's going to be very similar. So Control C and bring that here. And now we need to change a few things. Change that to read. Right, once that's changed, we need to change a few things here. We say not equal to end of file. And then these two lines, we'll have ch equal to getc, and we'll just put in the parameter fp. And this will become putchar ch, and that's all. Right? Now, of course, we can build this. And then go to the command prompt and we can run this program. So read a file. We get our error there. Press the up arrow and put in the name of the file. And there we have the file, right? Moving on now. feof. Use instead of eof when reading binary data. Returns true if end of file is reached, otherwise 0. The prototype, as you can see, returns an integer taking as parameter the file pointer. Write a program to copy a file. Let's go back to code blocks and we start a new file. So we start with hashtag include stdio.h and then hashtag include stdlib.h. Right? Int main, we have command line arguments. So int argc, comma, char star argv. And we need a file pointer, or two file pointers rather, file star fp, comma, out. Okay, this should be star out. Of course, that's a pointer. And then char ch. If argc not equal to, we need three arguments now. Remember, one is the program name, then is the source file name and the destination file name. So not equal to 3, then printf, then exit 1. The next check will be for fopen with the first file pointer. So if fp equal to fopen, and that file name is going to be in argv1, and we're going to open that in, remember that's on disk already, so rb, read binary. We're going to check if that's equal to null, then printf exit 1, right? Next is going to be for the next file. So that pointer is out equal to fopen, and that file name is going to come from argv2. We're going to open that wb, right? We're writing in binary. If that's equal to null, then printf error opening destination file, right? And of course exit 1. Okay, we've gone through all the checks now. Now we can proceed to copy the file. While, and we'll use feof, of course, while not feof, fp remember is a source file, or the pointer to that source file, and ch equal to, you can use getc or fgetc, whatever you like, fp, and then we can check if not feof of fp, then only write that to the file. So putc ch, comma, out, right? So we're copying character by character there, and of course that loop will continue until the end of file, when we will close both files. So fclose fp and fclose out, right? So now we can build this, and let's go now to the command prompt, and we can execute this. So here we just say create copy, and of course we can try our errors, and you can see their source file and destination file names required. Press the up arrow to go back to the command and provide the file. So let's just call that output file. We got that error because we didn't provide the source file, right? We provided the destination but no source. So go back, create copy, and new file, and then output file. Type output file, and there you can see our contents, right? Moving on now, working with strings. We use fputs and fgets. They're the same as puts and gets, except of course we're writing to files. The prototype int fputs const char star str. So this is taking as argument a pointer to a string of characters, right, and the file pointer. char star fgets. Now fgets returns a pointer to a string of characters. It takes 3 arguments. We have pointer to the string of characters, the length, that is the number of characters we want, and the file pointer. Right? Now in terms of fputs, it works like puts, but of course writes a string to the specified stream, and fgets works like getc, but we are reading the string from the specified stream. What about the return values? As I said, it returns integer. That integer would be a non-negative, mostly 0. It is if successful. If unsuccessful, it's end of file. What about fgetS? FgetS, if successful, returns a pointer to the string of characters, which will be our str1, for example, that we have in our code, or it will return a null pointer. So now write some code, write a program to read strings from the keyboard and write them to the file. So let's go back to code blocks and start a new file. Hashtag include stdio.h and then hashtag include stdlib.h. And we'll need string.h as well. So now here we have int main, and again we have command line arguments. So int argc char star argv. File star fp char str1, that's going to be 80 characters. If argc not equal to 2, then printf exit 1. Right? Then we need to check for fopen. So if fp equal to fopen, and of course the file name coming from argv1, we're going to open that in w plus mode. I'll tell you why a little later. This is going to allow us to write to the file and then read again, right? So w plus mode, if that's equal to null, why we're using w plus will be clearer after this program. Printf exit 1. If that goes through, let's have a do while loop this time. So we say do, and we're going to use getS, and then str1 and string cat. Now what are we doing with string cat? We are forcing that \n. Okay, remember I spoke about text streams having an optional \n. Remember getS does not include that as part of the string. So we are pushing it into the string, comma, \n. Then we use fputs, str1, comma, fp, and that's all. So now we are writing to the string. This continues as long as star str1 is not equal to \n. Okay. And now, of course, once that loop exits, we will close the file. Right? And that's all. So now we can build this. Then go to the command prompt. And now, of course, we can execute this. So write str strings or string file if you want to call it that, waiting for input. And that's all. Now if I type, you see the contents there, right? Now why did I use W plus? We'll see now. Moving on, rewind. So rewind allows us to reset the file position indicator to the beginning of the file. Prototype is, as you can see, returning void, that is nothing, and taking as parameter the file pointer. Now what we're going to do is we're going to go back to the code and modify it so as to use rewind. And therefore we need W plus, because now what we're going to do is after this, instead of closing the file, we're going to say here rewind fp. And once we've rewound that file, we can then proceed to reading it. So we can say here, while not fpof fp, and now we can use fgetc. fgetc. Remember, we need to specify the pointer to the string of characters. That's a string. Very simply put, number of characters is 30 and the file pointer. And printf %s, comma, str1. Right, so at this point now, the file position indicator will go to the top of the file and start printing out the strings, and then of course we'll close the file. Let's build this now. Now we can go back to the command prompt and run it. Right, and you can see how that was displayed on screen twice, because here we have used rewind and therefore it's displaying those characters on screen. So I hope that's clear. Moving on. Ferror, used to determine whether a file operation has failed, should be called immediately after each file operation. Why? Just consider this. Let's say you execute a read on a file, right? And then there is an error. And then you're executing a write on the file and there's an error again. The error after the read, if you don't check for it, is lost, right? So it's kind of in limbo there. Returns true if an error has occurred during the last operation, otherwise false. The prototype in ferror, file star fp, returning an integer. Now write some code to replace spaces in a file with hyphens. So let's go back to code blocks and start a new file. We start with hashtag include stdio.h and hashtag include stdlib.h. int main, and then file star fp star out. Okay, because that's the file that's going to have the hyphens. Char ch, and we have if fp equal to fopen, no command line arguments here. We're going to open the file we created. So string file, comma, that's going to be in read. If that's equal to null, then printf, and of course exit 1. Next check is of course for the file pointer associated with out file. So if out equal to fopen, and here we're going to give our own name. Let's call that out file. And that's going to be opened in write mode. And that's equal to null. Hope you're getting the hang of this now. Then what we will do is printf exit 1. If that goes through, then we can use fpof with these files as well. So while you will see that we can use fpof also when we don't use read binary or write binary. So while not fpof, fp, and within this loop we can see ch equal to getc fp. And then if ch equal to space, then we want it replaced, right? ch equal to hyphen. And now we got to write that into the new file. So putc ch out. Then we need to close fp and of course close out. Now of course we can run this straight away. We don't need to build it. Now we need to go to the command prompt and check whether the file has got the hyphens, right? So we can say here type out file, and there you see all the hyphens. Okay, so moving on now. Erasing files. Remove erases a particular file, return 0 if successful, else non-zero value. The prototype is int remove char star file name. So it's taking the file name as the argument, and of course returning an integer. Write a short program to erase a specified file after verifying that the user wants the file erased. So let's now go back to code blocks and we start a new file. We start with hashtag include stdio.h int main argc. We're going to have command line arguments to provide the file name. Right? No file pointer needed here. We do need a character because we're going to ask the user whether they want to erase a file or not. If argc not equal to, then printf exit 1. Now here we say printf ch equal to getchar, and then we'll say if to upper of get, or rather ch equal to y, right, then we can just erase the file. Remove argv1. That's all. So now we need to build this. Let's close this window and we can build this file. Okay, there seems to be an error here. All right. Int argc is what is missing there. Okay, we've got an error. And now you know why we need hashtag include stdlib.h. Okay, build it again. To upper again we're using. So what do we need? ctype.h. Right, build. And of course, that's gone through. So now we can go to the command prompt and try this out. Name of the program is ferase. Remember, we're using the exe file here, ferase, and the file name. What's the name of the file? Let's erase the one with hyphens. So out file. Are you sure you wish to erase? Yes. Now we can check directory out file, file not found. Okay. So that's about erasing a file. Moving on now. Flushing a stream. Fflush writes the contents of any buffer data to the file associated with the file pointer. As I said, we've already used fflush with stdin, but it can be used with the file. Fflush called with a null will have all files open for output flushed. Return 0 if successful, otherwise end of file. Now, the prototype int fflush, taking as parameter the file pointer. We're not going to write any code for that because that's pretty simple. Coming to fread and fwrite, prototypes are size t fread. So that's going to return a size t type. Remember, that's an unsigned value. It's going to take void star buffer. We'll see what buffer is. Size t num bytes. Again, we'll see what that is as well. Size t count and the file pointer. Again, fwrite takes the same parameters as you can see as fread. Used to write data types longer than 1 byte. So now we're talking about integers, floats, etc. Returns the number of items read or written. Count is equal to number of items written. Okay, but count could be less than the number of items read if we reach end of file or if there is an error. Used mainly to read, write, user-defined types. Now I said it's used to read data longer than 1 byte. So I talked about integers, floats, etc. But also user-defined types like structures. For fread, buffer is a point to a place, or a pointer rather, to a place in memory that will receive data from the file. So that could be as simple as the address of a variable, right? And then size t num bytes would be the size of that variable type, right? So size of int or size of float, etc., or size of the structure for that matter. Fwrite is a pointer to the data that will be written to the file. Okay, so that's the buffer for fwrite. Now, before we go to writing some code to creating a mailing list, let me show you a short example of fread and fwrite, where we are just defining a double int and a long number. And then, of course, we are opening a file in WB plus mode. It's going to again erase any existing file and create a new one. And then, as you can see, we are using fwrite first, rewind, and then fread. So fwrite, again, remember, this is the buffer that we spoke about. This is num bytes, right? This is count, and this is the file pointer, right? So let's execute this now. And you'll see those values displayed on screen because we wrote them first, then use a rewind, and then read them out. Okay, so I hope that's clear. Now let's go write our program. We need to start a new file. Now, just to understand what we are doing here, create a mailing list, save it on disk, then display the list on the console. So we're going to have 3 functions, one which will allow us to enter data. We'll have another function that will save the data, and then another function that will display the data. So we start with hashtag include stdio.h, and then hashtag include stdlib.h, hashtag include ctype dot h. We're going to have three functions, as I said earlier: enter data, and then we'll have save data, and then we'll have display data. Right? Now we define our structure list type that's going to be available to all functions. Therefore, outside main char name, that's going to be, let's say, 40 characters, char street of 30, then char city also of 30, and then char state of 3. Just going to use a code for the state, and char zip, and that's going to be of 10. Right? We're going to define the variable here itself. That's going to be list of 10. In effect, we have a double dimensional array, right? 10 elements, each of them having name, street, city, state, and zip. Right? Int main. And here we have enter data, and then save data, calling these functions, and display data. We start by defining enter data. We need a counter to enter the details for each person. So int ctr, and then for ctr equal to 0, ctr less than 10, ctr plus plus. Within the loop, we'll have printf name, right? And then scanf. We can use a scan set here, percentage, because there'll be a space between first name and second name, for example, \n, right? Comma. Hope you remember this. How do we get the first element, for example, the name from that? So list of ctr dot name, right? And then flash stdin. Similarly for street, city, state, and zip. So printf. So now we have all the information. This will go on, this loop, that is, as long as counter is less than 10. Once we finish, we can just return. Right? So return, and that's all. Next function, save data. And we have here our file pointer, int counter, and we check fopen whether there's a null pointer returned or not. So if fp equal to fopen, I'm going to provide a name for our file. Open that in write mode. That's equal to null. then printf and exit 1, right? If that goes through, then we have our for loop for counter equal to 0, counter less than 10, counter plus plus. And here we have an if statement, if star list of counter, right, dot name, right? And we have another if statement. Right? So if, and here we are using fwrite. So fwrite, we need to pass in all the arguments, remember? So that's going to be our buffer first. So ampersand list of counter, that's the address, comma, size of struct list type, right? Then the next argument is count, right? So that's going to be 1 and the file pointer. If that's not equal to 1, remember when we're using fwrite, number of items written will be equal to count. So that's not equal to 1. Then printf, after this loop, we can close the file. So fclose, fp, and return. Okay, so that's save data done. I hope that was clear. Moving on to display data. So now we need to open that file for read and display the contents. So we need file pointer, file star fp, and we need counter. If fp equal to fopen, and the file name is mail list, and we're opening it in read mode, and if that's equal to null, it returns a null pointer, then printf exit 1. Then we have our for loop for counter equal to 0, counter less than 10, and counter plus plus. And now we use the fread. If fread, and again the buffer, so the address list of counter, in comma, size of struct list type, right, and then comma, count, that's 1, comma, file pointer fp. If that's not equal to 1, then we check if fpof of fp, right? Then we return. Otherwise, of course, we printf, right? So you got what we're doing here, right? If that's not equal to 1, then it comes here. If it's end of file, it returns. If all this is okay, then we print the details. Printf name, and then %s \n, comma, list of counter dot name. Printf, right? Now we can run this. Remember, we don't have any command line arguments here as such. So we can run this and see how this works. Okay, there's a semicolon missing here. Okay, another semicolon missing here. So this should be 0 semicolon. Enter the names now and all the details. Okay, now we are not getting the name. Why? Let's go and check that. Here we don't have an F flash. Right, so let's run this again. Right, and then it's displayed. So now moving on, random access IO. We use fseek, sets the file position indicator at a specific byte, helping to perform random read and write. Prototype is int fseek, returning an integer, taking as parameters file pointer, long num bytes, that's a long type, and int origin. What origin is, we will see later. Num bytes is number of bytes from origin. Return 0 if successful, non-zero if failure. Now these are the values for origin. Seek set would be 0, seek car would be 1, seek n would be 2. Right? So seek set would be start of the file, seek car would be the current position, seek n is the end of the file. Write code to use random access and read the mailing list file created earlier, displaying on the console details starting with the details of the fourth individual or the person, ending with the last person's details. So now let's go ahead and do that. We need to go back to code blocks and start a new file. Hashtag include stdio.h and then hashtag include stdlib.h. Then int main. And we have the same structure, so I'm going to copy it from here just to save that time. Right, so we have the structure there. And now we'll have we just have here encounter and file pointer. And then we check if fp equal to fopen, the name of the file, comma, read mode, if that's equal to null, then printf, and then exit one. Now we use fseek. So fseek file pointer, comma. Remember we have long num bytes. So 3 into size of struct list type, right? Because we want to read from the fourth person. So 0, 1, 2, 3, right? 3 into size of struct list type. And then from origin, which will be seek set. Okay, that's the start of the file. And then for counter equal to 3, we say, right? Counter less than 10, counter plus plus, right? And within this loop, we'll check if fread, and then of course we need to specify here the buffer, so ampersand list of counter, comma, size of struct list type, right, comma 1, comma fp is not equal to 1. Then we got to check if feof, right? Because remember, count may not be equal to the number of items or the return value if, of course, there's end of file. So that's what we're checking for. Printf. Otherwise, printf. And now we print the details. Name. Okay. So that continues. Of course, as long as counter is less than 10. And then we need to close file. So fclose fp. Right? So now let's run this. A semicolon missing somewhere. Right. Now we've got these printed out. From where? From Corey cast. So you can check that out. That should be the fourth one. Moving on. fprintf and fscanf, very similar to printf and scanf, returns integer, takes as arguments the pointer, a pointer to the string of characters, which of course is the control string, right? Not always the most efficient though, these two. Why? Because they require more overhead. Consider that we are putting in our format specifiers, right? And therefore they're not really preferred, okay, in terms of writing and reading from disk. stdin, stdout, and stdair all are streams, right? So these are standard streams. They're open automatically, closed automatically. They can be used as file pointers in any function, but of course these are not normal variables and cannot be used with fopen. So we cannot really open them and close them. That's all done automatically. Now, just to give you an example of both of these, fscanf, fprintf, and standard streams, just going to write some short code here. You need not write this code. Right, so your hashtag include stdio.h and then hashtag include stdlib.h. And then, of course, we need our main function. And this is going to have command line arguments. So int argc char argv. And here we'll have our file pointer, of course. So file fp. We need char ch and then str1 of, let's say, 70 characters, and that's all. We check if argc not equal to 2, then printf exit 1, right? Next check is for fopen. So if fp equal to fopen, and we have argv1 where we get the name of the file from, that's going to be opened in write mode. If that's equal to null, as in a null pointer is returned, then printf exit 1, printf enter a string, and here we'll have scanf, right? So instead of using scanf, we can use fscanf, and instead of using the file pointer, we can use stdin, right? And then we specify our control string, so %, and we'll allow entry until a new line character is entered, and then comma str1, right? Then we'll use fprintf and fp, comma %s, again our control string, and of course str1, right? And then of course we need to close the file, so fclose fp, right? So let's run this now, but of course we need to build this here because we run it from the command prompt. Going back to the command prompt now, the name of the file is fscanf, fprintf. Let's check if our error works. It does. Press the up arrow, and we can put in the name of our file, C file. Enter a string. Right? Now, we've supposedly written into C file, and there we have it. Right? So you see how that works. Now moving on. Standard streams. So I'm going to write another program now. Hashtag include stdio.h and hashtag include stdlib.h. Int main char str1, that's going to be 70 characters again, scanf %s, or let's just say %, let's allow entry until the new line character, comma str1. Then printf %s \n, comma str1, right? Printf, that's done. It's a simple string. If we just run this program as is, it's just a simple scanf printf program. It's not going to do anything great. If I just type in this is a string, that's what I get, and that's all. But what I can do is, if I go to the command prompt now, and I use the operating system commands to copy from the console to a file. So let's just call it ifile. Whatever I enter now will be put into that file. So this is a demo of standard streams, right? And I press enter, and then I press Ctrl Z to indicate end of file. And if I type that out, I will have that string in the file. Now I have that file. Now what I can do with standard stream is something like this. I can say take the input from this file. I have a scanf there, but the input will go from this file, and then print the output. So let's try that. So if I take the name of the file now, it's called std_stream. That's an executable file, remember. And I say take input from I file and put the output into O file, right? Now if I type out O file, that's what I get. So you see it's taken the input from there, and then of course printed the output on, of course, rather to this file, and then of course we printed it out on screen, right? So I hope that's clear. Moving on. Redirect standard streams. We can use the freopen function, and let's see how. This associates an existing stream with a new file. The prototype is returning a file pointer, as you can see, taking the file name as argument along with the mode, right? And the stream as well. So I just have a short program to demonstrate this. I'm going to go straight to that file, and you can see here we're using freopen. We're opening out file in write mode, and the stream is std out, right? So we are redirecting whatever should come or be displayed on screen to out file. So let me run this now and show you the results. Okay, so if we go now to the command prompt and we type in out file, you can see we get the results there. So this ends our session for today. In the next session, we'll be talking about the preprocessor. Till then, take care, stay safe. Bye.